International University. This collaborative project with CMAS University of Miami is funded by JTTI. The goal is to have a 3D turbulence scheme in operational HAFS to enhance models' performance as model resolution increases to 1 to 2 kilometers or even higher in future. The project involves a close collaboration with EMC, LML, PSL, and GFDL, in particular Xu Jun, Bing, Tunkai, Zach, Fenglin, Jianwen, Locus, and Kwon provides a lot of help. Next. This is the outline of my talk. First, I'll give an overview of a 3D scaleware TKE scheme, and then I'll show some initial evaluation results of the scheme in HAFS operational forecast setting. And finally, I'll talk a little bit about the transition from research to operation at the EMC. Next. Let's first look at how turbulence is parameterized in numerical models. In mesoscale and large-scale models, the horizontal and vertical turbulent mixing is parameterized separately, with the former being handled in the dynamic core of the model and the later being treated by a standalone windy module outside the die core, known as PBL scheme. There are several reasons for this separated parameterization. First, the unresolved large ADs are anisotropic. They induce directionally different turbulent mixing. Second, the vertical gradient is much larger than horizontal gradient, so it is scientifically sound to separate horizontal and vertical turbulent mixing separately. Third, other model physics, such as radiation microphysics, are also parameterized in the same windy framework, so different model physics can be bundled together in a so-called model physics package, such as CCPP. Finally, there are unique vertical turbulent processes associated with shallow cumuli, stratocumuli, and non-local mixing. It is relatively easy to handle them in a windy framework. For a high-resolution model that explicitly resolves large ADs, known as large AD simulations, the horizontal and the vertical turbulent mixing is treated three-dimensionally as a whole in model's dynamic core. This is because unresolved small ADs are anisotropic, and they induce horizontal and vertical mixing cannot be artificially separated. For models with a great resolution in the gray zone, the unresolved turbulent ADs possess both anisotropic and isotropic characteristics. The 3D turbulent scheme using LES cannot be extended to the gray zone because they lack the ability to consider the anisotropic large ADs. So the separated parameterization are currently adopted to treat the turbulent mixing in the gray zone, but this creates a problem. First, as the resolution increases, the unresolved ADs tend to generate interconnected horizontal and vertical turbulent mixing. It is no longer scientifically sound to separate them. Second, the 3D shear production of turbulence becomes increasingly important as the resolution increases, but it is not considered in separate parameterizations. Next slide. So funded by JTTI, we've developed a 3D scaleware TKE scheme applicable to gray zone. To understand how it works, let's first look at how turbulence is parameterized three-dimensionally in LES. A turbulence scheme is to parametrically determine the tendency terms in yellow in the governing equation. A common method is to link the turbulent fluxes to local gradient via AD diffusivity Km, known as K closure. In 3D Smagorinsky scheme, Km itself is a function assumed to be function of local 3D deformation, where Km is the same in all directions because of the isotropic turbulence. In 3D TKE schemes, Km is parameterized in terms of TKE, which is determined by TKE budget equation. Using K closure, the shear production term can be expressed in terms of isotropic Km by this equation on the screen. In windy schemes, only the terms in yellow is considered, but this formula cannot be extended to the gray zone because turbulence is no longer isotropic. Next. So we need to reformulate the local K closure so that it can represent the anisotropic eddies in the gray zone. Unlike the isotropic turbulence, which generates the same Km in all directions, the anisotropic eddies result in directionally different turbulent mixing, where Km is a function of shear direction. Then we can rewrite the shear production in terms of direction-dependent Km. Assuming that all eddy diffusivity associated with horizontal shear are the same and all eddy diffusivity associated with vertical shear are the same, the shear production can be simplified by the equation where the Kmh and the Kmv are the horizontal and the vertical eddy diffusivity in the gray zone. They can be determined by blending the eddy diffusivity at the LES and mesoscale limit via a partition function, which is a function of the ratio of model grid spacing to the scale of large eddies. At the LES resolution, eddies become isotropic. Then the partition function becomes 0, and the direction-dependent Km becomes isotropic Km. Next. The scheme considers 3D TKE turbulent transport and pressure correlation in X, Y, Z direction, and considers non-local mixing in the gray zone. The scheme also retains the top-down forcing boundary turbulence associated with shallow clouds. Next. Finally, the treatment of horizontal mixing. HAFS uses a F3 dichrome, which uses the so-called divergence damping to account for the horizontal diffusion of the terms in yellow. It consists of first order and high order damping. The damping coefficient of first order damping is parameterized by the divergence and the vorticity, which is similar to the 2D Smagorinsky scheme. Note that the HAFS uses a 1D EDM TKE scheme to parameterize the vertical mixing. So in HAFS, the horizontal and the vertical mixing is treated completely different, independent, but this does not truly reflect the interconnected turbulent mixing in the gray zone. So now let's compare the FV3 divergence damping with horizontal diffusion formulated with K closure. We see that the first order damping is equivalent to the yellow terms in the governing equation using K closure. This provides a way to parameterize first order damping using the predicted TKE consistent with vertical diffusion parameterization. For this version of 3D scale-aware TKE scheme, we leave high order damping term untouched, but we are working with GFDL to explore the possibility to replace the divergence damping with horizontal diffusion formulated by 3D K closure in FV3 dichrome. Next. We implemented the 3D scale-aware TKE scheme in operational HAFS v2. EMC created a branch with 3D scale-aware TKE scheme on HAFS v2.01, which uses the new operational real-time ocean forecast system version 2.5 and conducted 2 sets of parallel experiment of simulating 2024 storms on WCOSS2, which named as HFXR and HFXT. They are exactly the same, except that HFXT activates the 3D scale-aware TKE scheme. The table here summarizes the simulated 2024 storms in the Atlantic Basin, in total 266 simulation cycles. Next. This slide shows a bias error of predicted storm track. There is a noticeable improvement in storm track forecast by the 3D scale-aware TKE scheme, particularly in day 4 and day 5 forecast indicated by the blue line. Next. This slide shows a bias error of predicted maximum winds. The performance of the 3D scale-aware TKE scheme is kind of mixed, but the scheme somehow relaxes negative intensity bias by HAFS and shows some improvements, the skills in the later part of the simulations. Next. This slide shows a bias error of predicted minimum storm center pressure. Again, we see improved skills by the 3D scale-aware TKE scheme in day 4 and day 5 forecast. Next. This slide shows the bias error of predicted storm structure measured by IMW, 34 knots and 64 knots radii. The 3D scale-aware TKE scheme reduces the bias in IMW, but generates a slightly larger bias in 34 knots and 64 knots radians. And these experiments are just finished. We are analyzing simulations now. Next. We also compared simulations with tail Doppler lidar retrievers. This is a Hurricane Milton simulated by HAFS V2 on Orion in total 8 cycles. The left panel shows the simulated storm track and intensity compared with the best track data. The right panel shows the simulated 1 kilometer altitude tangential wind and radiance height structure of a diurnal mean tangential wind compared with tail Doppler lidar retrievers. The wave number 1 asymmetry and the radius height structure of tangential wind simulated by the 3D scale-aware TKE scheme are closer to lidar observations. So the results are very promising. Next. The transition of the 3D scale-aware TKE scheme from research to operation at the EMC is now underway. Dr. Chengkai Wang at the EMC has been assigned to the project to facilitate the research to operation transition. The transition of this year focuses on HAFS. The implementation is completed and evaluation of the scheme in operational setting has been started. The transition to GFS will be taking place sometime next year. So in summary, a 3D scale-aware TKE scheme has been developed and implemented in HAFS. The initial evaluation results shows that the scheme improves HAFS skill in predicting storm track and intensity to some extent. For future work, we will further refine the scheme based on the simulation diagnosis, and will continue working with EMC for research to operation transition. Yeah, this is all I have. Thank you.
Thank you, Ping. Please stay on for the questions and answers towards the end, okay? Thank you. So the next speaker is Kate Musco of Sierra from Colorado State University. She's going to talk about improvements to the tropical cyclone wind speed probabilities.
Are we all set?
It's not full screen for the people online, even though it is in the room. It likes to do one or the other.
All right, I'll start talking about I've got a long title here. This was actually a Jetty project that actually finished up at the end of this summer, so the end of July. And the short version of this is it's dealing with WTCM and WSP 2.0, really getting down to the surface wind fields. And a long list of authors as well on this. This is a large effort between CIRA, NHC, National Weather Service, NCAR. There's a lot of people involved at this point because there's many different aspects of these products. It's not just the development, the implementation, new products based off of it, the social science aspects getting into even the color choices of the products and what forecasters want, what end users want. There's a lot of moving parts. Are we set? Okay, then next slide, please. All right, so getting into, I need to be a little bit taller. Getting into the project goals and objectives. This is the Jetty part of the wind speed probability and WTCM project, because the overall scope of this goes beyond the Jetty project as well. But for the Jetty project, oh, thank you. We were looking at generalizing the wind speed probability model. And really this is getting down into, the wind speed probability models I'll discuss on the next slide. It's got 1,000 realizations generated from the standard error distributions for the last 5 years of track intensity and wind radii. getting into this project was replacing the core of that with WTCM, which I will also get into in a later slide, which is really doing full 2D model fields from the WTCM model as the 1,000 realizations. And this project is, one of the goals is to make the wind speed probabilities consistent with the WTCM. And looking at perturbations, looking at dynamic model uncertainty, as opposed to the climatological error distributions. Updating WTCM, adding the exceedance products, which I won't show in this one, it's been covered previously. Looking at the gust parameterization and coordinating with P-Search. So next slide. Let's just say there's more slides than minutes. So the wind speed probability model, you might also hear me call this the legacy model. This is the currently operational version of the wind speed probabilities at NHC. Been around for almost 2 decades at this point in operations. And I'd already mentioned Monte Carlo sampling, going off of the previous 5-year error climatologies, and with some adjustment based off of GIPSY for the track. The wind structure, the radii, is using radii clipper. And then, 34, 50, 64 knot wind radii that we're looking at here, and the probabilities of being within those, and time of arrival. So the earliest and the most likely. Next slide. The WTCM, as I was saying here, is actually producing a 2D wind field for the surface winds with reductions over land. So this is using a surface layer that has 16 different land surface types included within it to try and have more realistic surface winds over land, as opposed to the over ocean that we were seeing in the legacy wind speed probabilities. So, this has been calibrated using ASOS stations, weather flow data over landfalling storms over the last several years. And again, getting back to the consistency, it's also being evaluated for being used within P-Surge so that you can actually have consistent wind forecasts and surge forecasts based off of that wind structure. Next slide. So this is the next generation of the wind speed probabilities. This is a comparison. It's not just the models being replaced. There's a lot of other things going on. One of the more notable is we're increasing the resolution from 50 kilometers to 5 kilometers, which makes a big difference. And you can see an example on the right of the operational wind speed probabilities versus WSP 2.0. Now, there's a lot of questions about the messaging of this and what it means to see those sharply reduced winds over land. And so there's a lot of work going on that end, and also evaluating point-wise versus area probabilities. There's a lot of areas still being investigated. But it also produces all the current products for the wind speed probabilities, adds in the exceedances. We're also looking at some additional enhancements in the future, one of which I think Mark is going to talk about later this afternoon, which is TCane. And then also looking at topographic effects, because obviously we've seen that this year. But that's been a long-standing wish list to add in, and the gust parameterization, which I'll show an example of here later. Next slide, please. So just jumping into some of the things that have been done so far within the JETI project, and a little bit around the JETI project as well. This is looking at the perturbations. So one of the things we did with the JETI project is pull out the perturbation scheme from the wind speed probabilities to actually run the WTCM realizations with those perturbations. In doing that, we decided that the perturbations could use a bit of help in how they were designed, because right now, just randomly sampling from that distribution of errors, you can get a lot of jumpiness in the tracks and things that don't look very realistic if you look at them on an individual track basis as opposed to 1,000 realizations. So one of the things that John Martinez is looking at is Jeff Keppert's method of dealing with the jumpiness in those perturbations. Next slide, please. So this is just an example. John gave a talk on this at the HFIP Telecon back in September. And, you know, on the left here is the original perturbations, and you can see a lot of sharp turns, you know, even within a 10-member set here, that not all of them look entirely realistic. And then you can see the smoothing that the Kepler processing is doing on the right-hand side. Next slide. And then this is just a further version of this, where you've got the original perturbations with the Kepler post-processing on the left, and then skipping the original part and just going with Kepler's method on the right, where you can see a narrowing there. So all of this is being evaluated within the context and making sure that we maintain the same distributions. Next slide. This is another different aspect of this. Alan Brammer has been continuing this work that was actually based off of work we did with the legacy wind speed probabilities back in HFIP, where we're substituting in the global ensembles and super sampling the GEFS and the EC ensembles to generate our spread for the perturbations, as opposed to the climatological distributions for each case. So right now, this version that he's testing doesn't include any accounting for the intensity bias in those ensembles at this point. But, you know, that's being evaluated as a precursor step or a complementary step to what Mark might talk about with using the uncertainty coming out of AI methods based off of models. So on the next slide, please. This is just an example. On the left is using the global ensembles, and on the right is using the standard Monte Carlo approach. And you can see a reduction in the overland probabilities being reflected, and the tracks of the global models taking it further on up and to the left over land. So next, moving on to the next one, gust parameterization. So this is a simple gust parameterization that is being evaluated for inclusion in the WTCM. And this is actually using the AWIPS gust parameterization method. And that is just a very simple wind speed based gust factor. Again, this is a starting point. There is a much more in-depth gust projects going on right now for evaluation. That is, I think Mark's going to discuss that in February at the HFIP Telecon. So next slide. All right, and then we get to some of the work that is going on with the storm surge unit. This is from Andy Penny, looking at the wind fields and the slosh versus the WTCM. And evaluating, in this case, that pink line that you're seeing in both of those plots is a cross section between the storm center and the Tampa Bay area. On to the next slide. Or yeah, click once more, please. There we go. So just looking at those radial wind profiles on the top right, you can see the difference between the slosh and the WTCM. And looking up to the point where it's just hitting Pinellas County there, that's where that dashed line is coming into play on that top right. To the right of that, if you're distracted by the dips in the blue line, that is actually the overland versus overwater in the Bay Area. So the water between Pinellas County and Tampa, and then between Tampa and the rest of Hillsborough County, that you're seeing those. So one of the things that we note, those dots that you're seeing on the top right panel, you know, with your RMW and then your wind radii, the slosh model is a lot closer to the RMW, especially now because it's set to the best track RMW. And the WTCM is a lot smaller in terms of the RMW. However, it is a lot closer to the 34 knot wind radii. And then you can see on the bottom right the observed winds. So next slide, please. This is just a continuation of that, where you can see that in general with the RMW, the WTCM RMWs are too small, and the slosh are pretty much right on the dot by definition, basically. And as a result of this, we're actually assessing how the RMW is being handled in the WTCM and potentially better ways of doing that for the inner core. Next slide. However, on the outer core, the WTCM you can see is basically on that one-to-one line with the actual best track 34 knot winds averages, whereas the slosh model is too small. So looking to basically come up with the best of both worlds going forward for both the wind and the surge. Next slide. All right, current status and transition plans. So, you know, at this point, we've got the WTCM. It's a standalone model. It is also a component of this new wind speed probability, this WSP 2.0. The WTCM is currently running in real time in development. So it's being transitioned in the spring. So in February, NHC will turn the code over to NCO, and it will be transitioned for the next season into operations as a standalone model. Wind speed probability 2.0, that is going to follow in the next year, at least for parallel testing. The operational transition is to be determined, and a large part of that is actually going to be determined by the moratorium on WCOS at this point. But right now, we do have things running on WCOS on the dev side, and things will be transitioning over. And we have things running locally at Sierra in real-time demonstration and being posted up to our real-time page. Next. So as I said, there's a lot of moving parts with this. So there's been a lot of presentations by various partners in this, focusing on different aspects. And there's more coming up, obviously, with the NOAA Hurricane Conference. And then also, we've had annual workshops preparing for this, introducing it to forecasters, doing training, determining what products are wanted. And another one of those will be happening in this spring in the March timeframe. So the work continues on. The JETI aspects have been completed for this, and then the transition aspects are following. And next, yep, I've got a future work slide. So things that we're continuing to work on, we're expanding the verification programs with this, assessing point-wise versus area probabilities, things like that. And, you know, this is getting towards some of those things I'd already talked about, assessing TCANE and looking at the more sophisticated gusts approach. Topography remains a large topic. And, you know, continuing the coordination and preparing for the deliveries. So that's it for me.
Thanks, Kate. So we'll move on to the next presentation. It is again online presentation by Rob Eicher. He's from Emory-Riddle Aeronautical University. He'll talk about the probabilistic intensity forecast products for the landfall and cyclones.
Good afternoon. Yeah, this project is a social science project, basically to develop.
Hey, Rob, can you hold on for 1 second, please?
Yeah.
We lost the TV here.
Make sure it didn't get. I think it might have gotten stepped on and pulled. I think it might have gotten stepped on and pulled the cord. Okay. And I think it just did the two screens. Yeah, it was close. Yeah, this one here. Okay. Whoops. Okay.
Okay, you should be good to go now.
All right, thank you. Again, my name is Rob Eicher from Embry-Riddle Aeronautical University in Daytona Beach. This project is basically a social science project designed to see what works and doesn't work when trying to communicate some of those probabilities from the WSP that Kate was just talking about. Our research team is a mixture of meteorologists, communication scholars, and an undergraduate research assistant who's a little bit of a mix of both. Next slide, please. Go back in time before this was even a JTTI project. It actually began with a conversation I had with my colleague Dan after Hurricane Laura in 2020. Initial forecasts showed it would be a 75-mile-per-hour hurricane in about 120 hours, somewhere near the northern Gulf Coast, as you probably remember. But if you read the forecast discussion, then you would have seen that the possibilities were all over the place, from it completely degenerating to being one of the major hurricanes. So next slide, please. And we kind of wondered, well, there really should be a product that describes that, right? Something that shows a range of possibilities for intensity, kind of like the forecast track cone there shows a range of possibilities for the track. Next slide, please. So my colleague Dan got in contact with some folks that he's worked with before down there in Miami at the National Hurricane Center, and they said, yeah, Ben Trading has actually been working on something like that. And I think Ben's on the call, so he can tell you a little bit more about the actual development of the product. But as you might remember, there used to be about 10 years ago a table product that looked like that table there on the right side of your screen. That showed the probability of various intensities at very, very specific hours. That was discontinued in part because users would misinterpret what they thought was a landfall intensity. So the product that Ben was working on was specific to landfall, figuring out the intensity at landfall specifically. Next slide, please. So these are the prototypes that Ben originally created and then sent to us in our project originally, before this became a JTTI project, was just to see, test these products on Florida residents and see what worked and what didn't work, what they understood and what was not so clear. In the prototypes, there's a couple different versions. One, any coastline that had any chance of landfall was outlined in that kind of orangish color, and accompanied by either a short table that had just the strongest reasonable intensity and then the chance that it would make landfall at that location. And then a longer table that had the probability of everything from tropical depression all the way up to major hurricane. And then other versions where the coastline was color-coded depending on how likely it was to make landfall there. Next slide. And what we found when we surveyed about 1,100 Florida residents is that some probability information seemed to be helpful, but there was definitely a point of diminishing returns. But we also asked the survey participants what they would want to see, what information is most important to them in a product like this. And overwhelmingly, we found out that they wanted to know the possibility of strongest intensities, and they also wanted to know what the strongest possible intensity could be. So we thought we were on the right track in creating a product that was going along those lines, but the longer table version that did not test well on many of our measures. It seemed like that was just information overload, and we'd ask people questions about that, and they weren't able to correctly answer. So they obviously weren't correctly interpreting the probability information there. Next slide. So then we got funding as part of the JTTI project to try to improve those products, those original ones, and see if we could make one that maybe worked a little bit better and see what worked and didn't work. So we assembled some focus groups of broadcast meteorologists, NWS meteorologists, risk communicators, some emergency managers, and even some graphic designers. And they helped us come up with the next versions. Next slide, please. And some of the modifications were simple. We can see the color coding there in the table, making the text a little bit brighter, easier to read, moving the legend to make it more prominent. But we also heard from our focus group members that it might be easier for the general public if that information was displayed graphically rather than the table. So we transformed that probability information into a categorical map, and that's what you see on the right. Next slide, please. We also heard from our focus group members that maybe this graphic should or should not have the cone. Some thought, well, this is an intensity product, not a track product, so leave the track off there entirely, just make it an intensity graphic. Others said, no, you need the cone on there to kind of provide that context. So we made two different versions, one with and without the cone. And we ran the tests again. Next slide, please. So in this case, it was just over 600 Florida residents, and the survey was conducted in 2023. Next slide. And what we learned, and this was encouraging, when we asked them questions along the lines of, do you think you understand this graphic? Do you think you could paraphrase this graphic, the information in this graphic? The results were similar to the currently operational forecast track cone. And we tested against the forecast track cone, not because this graphic is supposed to replace the forecast track cone in any way. It was just that we wanted a baseline for a comparison. And since that's the most viewed graphic that the Hurricane Center issues, we thought, well, that's obviously the gold standard. So we were somewhat encouraged by the fact that a graphic that has been in use for over 20 years and every Florida resident probably recognize was just as understandable as our brand new prototype that had all this new numerical information in there. So that was encouraging. Next question. Then when we gave them a quiz and asked them questions like, where is this most likely to make landfall? How strong is it going to be when it gets there? And other questions about the actual forecast. Those that saw the prototype graphics were significantly more likely to answer those questions correctly, which makes sense because the only intensity information in the forecast track cone is those little H and M symbols there. So they were better. The participants actually understood the information in the table, correctly interpreted it, and got more information out of it, and were more likely to answer the questions correctly with the prototype. So that was encouraging. Next slide, please. In general, we found that the longer table version didn't test well on most of our metrics, despite our efforts to make it better, to make it more understandable. In many ways, we only made it less so. So that one didn't seem to work for most people. But again, when you give them that shorter table version, most people were able to comprehend that additional probabilistic information. And that's information that they desired, that they actually wanted to see in a forecast product. But next slide, please. Unfortunately, there may not be a silver bullet answer to this question. We also separated by numeracy skills as part of the second round of surveys. We asked them questions like, how comfortable are you calculating a tip? How comfortable are you with percentages? And those that scored in the top third of that numeracy scale, so those that said they were very comfortable with numbers, actually preferred the longer table version. They better understood that one than any other prototype. And those on the opposite end of the scale, on the low end of the numeracy scale, so those that said they weren't very comfortable with numbers, did in fact just like the map version, the categorical color-coded maps rather than the tables. So that kind of tells us that, yeah, we may not be able to find a single graphic or create a single graphic that answers all these problems here. Next slide, please. But this was encouraging. As part of that same scale, that numeracy scale, we asked them, when you hear a weather forecast, do you prefer predictions using percentages or predictions using only words? And about 34% said they only wanted the numbers. Majority said that they wanted some combination of words and numbers. And only 10%, 10.8%, said they just wanted the words. So in other words, roughly 90% of the people wanted some amount of numbers in their forecast. And next slide, please. And when we asked them, you know, do you have any comments about the presence of probability information in a weather forecast? The comments were overwhelmingly positive. We asked our undergraduate research assistant, who was blind to what we were doing, you know, asked her to code these and say, you know, tell us any comments that you think were overall in favor and any comments that were overall not in favor of using percentages. And overwhelmingly, the comments were positive. And these were just some of the comments that we got from the survey participants. Next slide, please. But the work continues. So we assembled, we felt like, all right, we're on the right track. Probability information seems to be a good idea. But work continues, and we assembled another focus group, again, broadcast meteorologists, emergency managers, National Weather Service personnel as well, and asked them to help us make the graphic even better. The survey, we didn't really get a definitive answer about whether this graphic should or should not include the cone. But overwhelmingly, the focus group participants said the cone is definitely needed, that need that track information along with the intensity information to give it some context. But they didn't like how we drew the cone, or at least how we created it. There were even some comments along the lines of Sharpie date. You can see there someone said it looks like a third grader drew it. Next slide. Again, the focus group participants were generally in favor of the idea. But again, we kind of got that idea that some of the emergency managers really liked the longer table version. They wanted to know every possible probability and every possible number that we could calculate. Whereas others thought, well, for the general public, that may not be such a good idea. Next slide. And they also provided some helpful suggestions, again, some ideas about the colors, some ideas about how we could organize the graphic, and that sort of thing, the wording as well. And that brings us to the current prototypes. Next slide, please. So this is what we're working with right now. We've got one version that has a map that shows probability of landfall, and then that information is highlighted in a table, and the table also includes the most likely wind speed and the strongest reasonable, which we call now the potential wind speed at landfall, so like worst case scenario wind speed. Next slide, please. And then we've got another one where the map actually shows the categorical intensity at landfall. So we got the most likely wind speed at landfall on the map, and then highlighted again there in the table, and then the strongest reasonable landfall intensity as well. And then finally, the map version of that is the next slide. A categorical map that again shows the probability of landfall on the left, color-coded most likely intensity if landfall occurs, and then color-coded reasonable worst-case intensity if landfall occurs on the right side there. Next slide. So our plan, now that we've got those ready to go, we're working on a third round of surveys, and this time we're going to do it outside of Florida. In addition to Florida, we're going to test it in several different hurricane-prone states. We're also going to do it in English and in Spanish. And we're also going to employ a broadcast meteorologist to help us test what this information might look like as part of a television weather broadcast, how these graphics might get used, or how this probability information might get used on TV as well. So that's all coming up in the next year. And then our goal is to provide the Hurricane Center with some recommendations on what works when it comes to communicating the probability of landfall intensity. Next slide, please. And before we test these, if anyone has any suggestions or any tweaks they'd like us to make on those prototypes, or any questions you want us to ask in the survey, please let us know. Thank you.
Thank you, Rob. Please stand for the questions towards the end of the session. Okay.
Will do.
So the next talk is given by two people, John Potterjai of the University of Maryland and Yu Yang of Oklahoma University. They talk about the data assimilation capabilities for the HAFS. John, you're going to share your screen?
Yeah, I'm going to just share. Just give me a moment. It's not full screen. Hold on one moment, please. It's going to be my entire screen. All right, so it should look better now. So I'm going to share this time slot with University of Oklahoma. And I'm going to apologize in advance. I have a lot of stuff to go over in just 7 minutes, which is my half of the presentation. I also want to point out that the title for this session is a little bit misleading. It's only my part. And so OU's contribution will be slightly different. And so this is a JTTI funded project that focuses on various data simulation developments for HAFS. To provide a quick overview of who's involved and what we're doing. First of all, this work is performed by 3 different universities: University of Miami, University of Oklahoma, and University of Maryland. For the UM side, their role is to help establish a mature JEDI-based data simulation system for HAFS, primarily focusing on the atmosphere. OU is bringing all sky radiance data simulation capabilities into HAFS, focusing primarily on GOES 16, which will be the topic for the second half of this presentation. And for the UMD side, we're focusing on bringing new DA capabilities into an experimental fully cycled ensemble system, which I'll talk about. And so in short, for the UMD side, our contributions are built on some past work that focuses on performing nonstop basin-wide data simulation first for the HWRF model and then for HAFS, as well as bringing in new DA techniques that focus on things such as bringing some non-Gaussian data simulation capabilities through particle filters into ensemble DA frameworks. And so for our work for HAFS, what we're essentially doing is we're taking our current operational setup, which is represented by this this dark maroon colors on the left over here for the domains, where we have this large parent domain and then a high resolution nest. And instead of working in this more complex looking framework where the domains are moving on us as the storm evolves, we're just using one fixed domain, which is given by this large magenta colored region. And we're performing just nonstop data simulation over a very active month of the 2022 hurricane season. And so that's our testing period, but we're doing, we're applying this framework for testing out a few different new DA methods. And basic idea for this framework is we're going to perform convective scale data simulation over this big maroon area, so down to 6 kilometer grid spacing, with a 6 kilometer grid spacing ensemble that feeds some uncertainty estimates into the DA as we go forward. All the physics that we're using for this model setup are identical to the 2023 operational HAFS-B setup, and so pretty much all the simulations I'm going to show are from those physics. And we're going to test out 2 different configurations for updating the ensemble part. One is using an ensemble common filter, and the other one is using the localized particle filter. Again, because we're doing everything over this pretty easy to understand setup where we just have one fixed domain. We can also do some things that are not typically done for the operational system, like perform our own online estimation of biases for clear radiance measurements. And so this is a very expensive setup and requires a lot of software engineering on our side in order to get it to work. And we're at the point now we're about halfway through our experiment timeline, and so we're testing this over about a month past the spin-up period for the month of October 2022, and focusing on 6 storms that occurred during this period. And what I'm going to do is show some results for the first half, which focus on Danielle and Earl. We're partway through Fiona right now for our experiments. And on top of doing the data simulation part of this, we're testing out 2 different workflows for incorporating these DA analyses into forecasts in a way that resemble the operational setup. The first one I'm going to call a self-contained workflow, in which we just take our output from this data simulation performed over this big magenta region and interpolate it onto a 6-2 domain setup where we have a 6 kilometer nest and a 2 kilometer moving nest that follows the storms from the forecasts. And so that can be done for either the deterministic analysis we produce or the ensemble members that we produce during DA. The other option is to perform what I call a parallel workflow, where we run this cycle data simulation system, and we simply feed in the bias correction coefficients from that part of the DA, as well as a high resolution ensemble into the operational workflow. And so one thing to note here is the current operational HAFS workflow doesn't use its own self-contained ensemble. It borrows the ensemble from the GDAS, so from the Global Data Simulation System. And so a major focus here is to feed in an ensemble that can give you the fine scale, mesoscale error covariances that are needed for the data simulation steps. Some quick results. First, I'm just gonna note, so on the left I have track RMSEs, and on the right I have Vmax RMSEs. They're a bit noisy because we're only 2 storms in so far. And I'm gonna highlight a couple things here. First, we have 2 sort of controls that we're looking at. One is the operational H4 from the 22 season, which is the light blue line. And the other one is the 2022 HFIP demo for HAFS, which is the closest thing we have to essentially the operational setup for the model in 2023, which is the version of HAFS that we're using for our experiments. And first thing I want to note is for track forecast, all of our setups can do better than the operational H4 for track past, say, 80 hours or so. And for intensity, we really struggle with the self-contained workflow. Likewise, the self-contained workflow has larger errors than this parallel workflow for reasons that will become pretty obvious in the next slide. Another thing I want to note is comparing our parallel workflow to what I'm going to call the future operational HAFS, which is the green. In terms of track, they're comparable skill, but we have slightly better skill for Vmax out past 80 hours, and so there's at least some positive benefits from feeding in a mesoscale error covariance estimate that we spinned up on our own. And I also want to note here that even if we don't do better than the operational system, it's still positive. The reason being that this mesoscale structure, or I should say our self-contained ensemble, that we use for spinning up the mesoscale error covariances, are really needed if we want to make progress in the long run for doing coupled ocean atmospheric data simulation or coupled wave atmosphere ocean data simulation in the future versions of HAFS. And so that's like a prerequisite for that type of research. In terms of the performance of our self-cycled experiments, the dominating factor that led to a degraded track and intensity forecast really came from these really large basin-wide biases that crept up in our experiments. And so here I'm just showing a quick verification from the data simulation showing the ob space verification of the background state. And so this is essentially a 6-hour forecast. And if you just focus on the right, I'm showing temperature bias for both the ENKF variational experiment and PF variational experiment. And both of them just have really large lower tropospheric temperature biases. And these are things that we didn't really see in previous configurations of HAFS that we did starting in 2020 for the pre-operational work. And so this is coming about due to either changes in the physics for the model or the fact that we're running this down this 3-kilometer grid spacing and turning off convection. And so either way, these biases are predominantly what dominate our results for our self-contained workflow experiments, and become really problematic for situations where the storm is undergoing extratropical transition or interacting with mid-latitude weather systems. And so I don't have time to go into details of that, but that's some findings that we have so far. And one last thing I want to mention is we're starting to now look at ensemble forecasts for our self-contained workflow experiments, because one natural benefit of this workflow is it gives you a self-consistent way of generating ensemble predictions. And so we're running 10-member forecasts, the 6-2 grid spacing configuration that I showed you earlier. And here's just an example of a bunch of ensemble forecasts that were run for Hurricane Danielle. And as it underwent extratropical transition, it's a very complicated setup. And then I want to show you the next slide, which is the same result, but for the particle filter. And I could toggle back and forth between these. And one thing I want to mention is one finding so far is this LPF, which is more of a Bayesian data simulation technique, actually gives you a better control over your ensemble spread. And this is something that we're actually exploring in a separate NOAA project for global scale data simulation. A lot of this comes back to preserving physical consistency in your ensemble updates in a way that kind of satisfies like more of something that looks like the Bayesian posterior that you'd expect during data simulation. But that's one positive finding so far. And so just a quick summary. All configurations we've tested capture basic features of TCs well. I didn't go into much detail of that yet. Parallel workflow shows benefits for intensity prediction, which follow from the fact that we're introducing, like smaller scale covariances during the DA optimization step. Cycling DA results struggle largely because of very large temperature biases that we find. We did some experiments with both HAFS A and HAFS B and find very similar looking results. Ensemble variance in the LPF is easier controlled than ENKF. And this is something that has implications for global data simulation as well. Next steps are to complete testing over the remaining storms. And also I'm working with NOAA PSL right now to bring this new data simulation system into JEDI. And with that, I'll hand things over to OU.
Thanks, John, for that interesting presentation. Can you try sharing your slides on your end?
Yes. Can you see my screen?
Yep, looks good. Thanks.
Okay, thank you. Good afternoon. My name is Yue Yang from the University of Oklahoma. I will introduce the direct simulation of GO16 ABI of sky references in HAFS self-cycle dual resolution inverse system. Previous studies have emphasized the importance of assimilating in the core observations to improve hurricane intensity predictions. The ABI of sky references with a high sampling resolution have the potential to improve hurricane forecasts. However, there exist many challenges on how to effectively assimilate ABI of sky references. OU MapLab have made many efforts to develop and optimize the ABI of sky references DA. For example, best correction, observation error estimation, issue associated with nonlinear observation operator, and hydrometeor-enabled vortex relocation. This presentation will focus on addressing the issue related to ABI nonlinear observation operator in HAFS. Using a standard state vector configuration for ABI of sky references DA, a nonlinear observation operator leads to cost function gradient imbalance and slow minimization in the inverse DA. Following the method proposed by Wang and Wang 2017 for direct radar reflectivity DA, directly including brightness temperature TB as a state variable can alleviate such problems for convective event. However, previous study only examined the TB state method when ABI of sky references are simulated alone. The limitation of standard state method and the effectiveness of TB state method have not been explored when ABI and many other observation types are simultaneously assimilated. In addition, the impact of employing TB state method to assimilate ABI of sky references on hurricane forecasts has not been studied. To assimilate ABI of sky references, we employed some DA capabilities in HAFS to establish the ABI enhanced HAFS self-cycle dual resolution inverse system. The hydrometeors are updated during DA. Our study is performed for Hurricane Laura 2020. The red line highlights the DA period, which is designed to capture the rapid intensification. Here are some specifics for the model and the DA configurations. We assimilate the ABI channel 10 Oscar references and all operational observations. Two experiments are designed to compare the performance of standard state and TB state to assimilate ABI Oscar references. The following are the results. Here shows the increments for different variables and the convergence level. From the first DA cycle, we can say TB state in the bottom row yields greater increments than standard state in the top row. In the right panel, TB state speeds up the minimization compared to a standard state. As an example, DA cycle valid at 12Z, August 25 is selected for 1 and 3 kilometer wind field compared to the observation in the first column. The analysis of TB state in the third column better capture the inner core dynamic structure and the storm location than standard state in the second column. In terms of the forecast from this cycle, we can say TB state, the blue line, improves intensity and the short to middle track prediction than standard state, the red line, as well as better capturing the rapid intensification. The stronger rapid intensification in TB state can be attributed to the stronger analyzed warm core structure. The track prediction are influenced by the steering flow from the western edge of the Atlantic subtropical high. We can say the accurate short to middle track prediction in TB state shows a close relationship to the large-scale environmental analysis. In the black box, we can say the high in state standard state, the thin red line shifts towards northeast compared to the TB state, the thin red line, consistent with the track patterns. The overall mean absolute errors for all cycles confirm the advantage of TB state over the standard state for intensity and the track predictions over during almost the whole forecast period. In summary, HAFS self-cycle dual resolution inverted system is further developed for Go 16 ABI Oscar references DA. The capability of directly including brightness temperature as a state variable is employed and compared with the method use standard state vector. Compared to the standard state, TB state speeds up the minimization in INVAR and the analysis fits closer to the observations. TB state also has higher scale than standard state for intensity and the track predictions. In TB state, the input large-scale environmental analysis contributes to the track prediction, and the stronger warm core analysis promotes the rapid intensification prediction. For the future work, the transitioning to JTTI is ongoing, and we plan to develop the online adaptive observation area estimation and online bias correction approaches for ABI Oscar references in HAFS. That's all I have. Thank you.
Okay, thank you. Thank you, Jonathan, and you. So the next 4 talks are testbed talks. Those are moderated by Jordan Dale, who is online. Over to Jordan.
Thank you, Chandra. Can you hear me fine in the room?
Yeah, sure. Yeah, we can hear you.
Great, thank you. As Chandra said, I'm Jordan Dale. I'm the Testbeds Program Manager at NOAA's Weather Program Office. Our next 4 sessions will highlight WPO-funded hurricane and ocean testbed projects. Our first presenter is Jonathan Vai from NCAR, who will share updates about forecasters support products for analysis of TCs.
Thanks, Jordan. I just want to acknowledge my full team, Eric Hendricks, Chris Rosoff, and from CSU, Michael Bell, Alex DeRosier, and Jen DeHart. And from University of Miami, Jun Zhang. I have a fantastic team, and I also want to acknowledge the NHC points of contact. It's just been great working with Wallace and Lisa's our point of contact over there, and the whole HOT team has been great. So next slide. Just launching in, the overview of this project is to implement a real-time suite of observational products, basically to support the forecasters at NHC. So this is something quite different. And just a little side story, the nexus of this project came about in 2016 when Michael Bell and I were at Puerto Rico at the AMS Hurricane Conference, and we were at the banquet. And we were just talking and thinking about our joint capabilities, and we're like, wouldn't it be great to join these together? So I just want to thank WPO for funding this work, which I view as a little bit more of a high risk, high reward type of a project, but it's turning into something really good. And so I'm just going to plow ahead because I know time is short. But the point is to make high quality spatial and temporal analyses of the TC wind field. And what we want to provide to the forecasters is graphical and tabular outputs for intensity, RMW, wind radii, and put this in a format that's really easy for them to grasp, and they don't have to wade through all the different vagaries of dealing with the observations that are often conflicting and sometimes hard to wrangle, because we know the forecasters are very busy, they're in a time-limited environment. So the point of the project is to implement, and automate all this so that I can help the forecasters. Next. Okay, so pictures are nice at this time of the day. There's been a lot of presentations, and the idea of this project is that there's a lot of data, rich data available from the flight level data and also from the tail Doppler radar, Doppler radials. And what we would like to do is blend this together and come up with a high quality analysis. So on the top of this figure, you basically have a spatial workflow. And this describes how we're melding these observations together using Samurai, Michael Bell's Samurai technique. And then we're taking the flight level winds, both from tail Doppler and the in situ obs, and we're reducing these with a wind reduction model, which I'll talk more about. And the final output is a nice, pretty picture of surface winds that we think are quite high quality. And so you can also get parameters out, like the key parameters, intensity, the max winds, RMW, et cetera. On the bottom side of this diagram, we also have a bunch of flight level data processing going on behind the scenes with automated center finding, radial parsing, and all that good stuff. And we're putting it through another type of analysis, which is temporal. So the idea is to get in time a nice picture of what's going on with these storm parameters to the best of our ability as much as the observations allow. Next slide. So the next thing I'm going to describe is CSU's part of this, which is the surface wind analysis. Next. And so the background here is just that we have wind ratios. We know that if you have a flight level wind and you have a surface wind, you can pair those up, computer ratio. And with dropsondes, this is fairly easy. However, the dropsondes are drifting in space and time. And so you can get a number, but it's not necessarily representative of a specific location. It's kind of a Lagrangian trajectory. But the point is that within the storm, these wind reduction factors exist. You could imagine point-wise at every single point in the storm. And we know that there's theoretical considerations. There's factors such as drag related to the storm translation, left-right asymmetry, and also eyewall slope. And then there's this wonderful instrument, which we heard a lot about today, called SFMR, which estimates the surface winds from ocean surface emissivity. And when we were putting this project together, we thought, wow, this is great. We could co-locate the flight level winds with SFMR, run it through the neural network, train it, and then we'll get this great pairing. And I think we even in the proposal might have called SFMR the gold standard, possibly. So it's funny how these things work, and then the science evolves, and you're like, interesting. So, but the bottom line is that it actually worked pretty well. So next slide. But first, we have to talk about a benchmark, because if you're going to do anything new, you have to compare it to something. And so the state of the art that we figured we should compare to was the Franklin et al. 2003 dropsonde profiles, where he came up with reduction factors for the wind. And these were meant to look at the peak winds in the storm. But we were like, okay, can we apply this in kind of a sane sense across the storm? And so that's what we set out to do. Alex came up with this, what he called the simplified Franklin benchmark. It's not perfect, but we know that there's left-right asymmetries and all that good stuff, but it serves as a pretty good benchmark. Next slide. So the next part of training this database was to put the winds into some sort of a framework that they could actually be trained on. And so to do that, you have to think about location, because we know that these wind reduction factors vary throughout the storm. There's a lot of different factors going on. And what we wanted to do is build a model that could actually take these into account. So it's put into a normalized polar grid space where radius is normalized by radius maximum winds and the azimuth is put relative to storm motion. Next slide. And then the neural network. I'm not an expert on neural networks, but they're great tools. What's interesting about them is that they are capable of learning from large and noisy nonlinear data sets, which is exactly what we had. So we decided that we would try this out, and Alex spent a lot of time trying different things. He tried predicting the surface winds directly, which didn't work too well. But then he also tried predicting the wind ratios, and that turned out to work pretty well. But there was still a problem. We needed to get the model to emphasize the high winds, because we really cared about when the SFMR and, you have this uncertainty between SFMR and flight level winds at high wind regime. How do you handle that when you only have, limited data? So Alex came up with a shifted cubic loss function, which essentially teaches the model to reward the high winds and not care so much about the low winds. And so he split up a 4-year period of this co-located data from Flight Plus, and he split it up into validation, testing, and all that good stuff. And he trained it. And the predictors were R star, theta star, flight level wind speed, the altitude of the plane, because we didn't want this just to be at one level. We wanted it to work no matter what level the plane was at. And the nearest best track Vmax, the storm motion magnitude, and flight level RMW. So not a long list, but some pretty good things that you can imagine would affect this. Next slide. Okay, so how did it do? So validation is yet another challenge. Whenever you're coming up with a new technique, you need to do something that's fair and accurate and not biased. So Alex figured that the best thing to do would be to compare the flight level winds from TC radar. So you take those Doppler winds and basically take those as if they're the flight level winds from the plane, or however you want to consider it, and then reduce those using the neural network and co-locate it with dropsondes. So he took the TC drops data set and he used the WL150 and got it down to a surface equivalent. And so that's what he used to calculate the error statistics. So there's actually no SFMR data actually being used in the validation. And the results were quite good. You can see the comparison between simplified Franklin and the neural network technique, and there's substantial improvements. Now, of course, there's room for improvement, but the thing that gave us good heart is that at the highest wind speeds, the improvements were the greatest. So that was exactly what we wanted to see. Next slide. Okay, so what do these products look like? So here are 2 example products that have been running in pseudo real time. Jen has been doing all the implementation and integration over at CSU. And she's been running some of these in cases, within like an hour or 2 after the data come in. So on the left, you see Milton. At this point in time, NHC analyzed 135 knots. And you can see the left side there is surface wind speed. The middle panel there is flight level wind speed. And you can see how these compare. And then on the right, you have the actual wind ratio. You also have the flight tracks that contributed for this 1.5 hour or 1 hour and 15 minute analysis period. And then finally, there's some tabular information down there that helps the forecasters just see at a glance, okay, what is the data showing, what is SWAN showing, and what would the simplified Franklin show, and what does SFMR show if it was there. So it wasn't there in that case because they'd already stopped transmitting, but for Barrel, we did have that. So moving over to the right side of that figure, this was a case where NHC and SWAN agreed very closely, and you can just see the richness and the quality of these wind views. It really looks like a nice picture, like you could imagine the wind field actually looking. And you can also see the warts of SFMR on full display. In this case, that's the black line. So you see those transects through the storm space. And SFMR kind of had almost equal left and right values across the eye wall, but the flight level was very different from that. And if you had just taken SFMR at face value and said, okay, this is our gold standard, that would have only given 111 knots, but SWAN gave 127. And that's probably a lot more realistic given the flight level winds. Next slide. Okay, TCOBs. I'm going to briefly talk about what we're doing at NCAR on the temporal analysis side. Next. So TCOBs is a framework that I developed back in 2016. And the point was to put in all these observations and almost like a new historical database, get out the essential storm parameters at 1 hour resolution, completely data-driven though, objectively data-driven. And that was done using these exponential temporal weight functions, which were criterion formed. You basically give it a target and set up a criterion. How close is the observation to this? And then how much does it contribute to the intensity upper bound, et cetera? And then you use the obs that are closest in time and you weight those more heavily. Well, we figured we should probably try to do something, see if we can improve on that. So that's what we set out to do in this project. And Eric Hendricks has been implementing this. What he decided to do was take a strong constraint 4D var type of approach, but instead of analyzing a 3D vector, we're just going to analyze this scalar value. So he calls this 1D var in time. And you can see the idea there is there's an assimilative window, and the 3 observations are the green dots there. And the blue is some sort of background, doesn't have to be the best track, it could be anything, whatever you decide is an appropriate background to use. And then the red is kind of the innovated output. So what you want is you want it to have some fidelity to the observations. Okay, next slide. So next also. So here's the full gory details. It's just like what you would expect from a DA method. There's a cost function, there's a minimization that's done, there's a forecast model and an update model, and it's all DA. So it's kind of cool to apply this in a very simplified framework where you can actually see what's going on in the whole equations. But these can be recast, and so the bottom right panel there, you can see there's 3 terms. Those represent the 3 observations. So those are the innovations to the model, and the beta terms are basically the weights, how you would compute those. And the cool thing about this is not only do you get this like central tendency estimate, but you also get a variance. So this can be thought of as analogous to uncertainty, which is pretty cool because now you can get time-dependent, observation-dependent uncertainty. Next. Okay, of course you have to specify errors. So just for now, we're using the HERDAT documentation background errors. And for the observations, we're estimating that those are twice, half the size of those. But the cool thing is with this rich mountain of data that we've collected, we can now do validation studies and pull out what these might actually be for different instruments and plug those in. We haven't done it yet, but that's something that we're looking toward the future. Next. Okay, how does it look? This is how it looks for TC position. This is Hurricane Isaac in 2007 and, let's see, 2012. And what's interesting is that if you shorten this window, you can capture these small scale fluctuations like trochoidal wobbles. But if you lengthen the window to like 10 hours, you get something that looks very much like the best track. Next. Okay, this is how it looks for intensity. The 1D var is on the right, and you can see that it has more small scale fluctuations, but it does seem to reproduce the best track a little bit better than these exponential weights from the original method. Next. And this is just the same thing for RMW. Next. Okay, wrapping up. So this is the planned implementation of what we plan to test for the temporal system in 2025 during the hurricane season. And so you're going to get all this real-time processing of the VDMs and the flight level data feeding in from one side. What we plan to do is use the Samurai numbers, which are, I think, of quite high quality themselves, and use those as the background. And then for each observation, we'll be able to plug this through this method. And the cool thing is the framework allows you to kind of measure the impact of each observation. So if we have a new instrument, we can compare and see, well, how much is this really affecting the analysis, which is quite cool. Okay, next. So just finishing up, for future work, we're going to be integrating all this and demoing it during 2025. Quantifying uncertainty is still a key task. We want to improve the center finding for the weak storms. That's a really important aspect that's a little bit infernal of a problem, but it's important. And then there's a wrap-up tasks. But looking to the future, we're thinking about next steps. We would like to take this project further in the future with new funding and look at IRAP and Kaya. And we think IRAP would have substantial benefits because it can get down to that 30-meter threshold above the surface. So you essentially could retrain and get a whole bunch of potential improvement, which we think would then feed into the surface wind field. So we know that this is a really key thing for NHC. The forecasters really care about the surface wind field, and that's where all the damage is done, as someone said earlier today. So it's a really key thing to push forwards. Thank you.
Thank you, Jonathan. All right, our next presenter is Mark De Maria, who will be giving updates about a machine learning model for estimating TC track and intensity forecast uncertainty.
Hey, thanks, Jordan. When I first started working at the Hurricane Center in the 90s, there's a forecaster there, Miles Lawrence. Some of the older people in the audience might remember him. One of his favorite sayings was that you can't say too much about brevity. So I'm going to take that to heart and try to hit the high points here since it's kind of late in the day. Oh, okay. Okay. So I'll use the time to explain the motivation for this project came from. Oh, okay. Yeah, the motivation came from, there's a faculty member at CSU, Libby Barnes, and she had done a lot of work to try to estimate the uncertainty of climate forecasts. So she developed an artificial intelligence method for doing that. And listening to her a couple of her seminars, it looked like, we could apply that to the short-term hurricane forecast problem as well. And so that led to this HOT project that involves a combination of Sierra as well as Libby and her group. Next slide. So I'm going to talk briefly about the tropical cyclone artificial neural network error model, TCANE. We ran this in quasi real time in 2024. I'm going to show some results of the sample products and the verification, and then where we're headed next. The next slide. The other motivation for this is that there's a lot of products on the NHC website. I just grabbed this from Hurricane Helene, and most of these are probabilistic based. The probabilistic storm surge, wind speed probabilities, some of the things that Kate talked about, as well as the product that Rob talked about in his talk, that's also based on the wind speed probability model. But the uncertainty in that just nearly all comes from the past 5 years of NHC's forecast errors. So there's not much or next to no ensemble information in there. There's no situational dependence. And so what we're trying to do with this project is to figure out a way to get that information into some of these public-facing products, but also maintain consistency with the NHC official forecast. And that's really one of the difficulties with using ensemble information is that if the ensembles, for example, tend to have a low intensity bias. And so the ensemble products would be totally inconsistent with NHC's official forecast. So this machine learning method is a way to correct for that and actually take ensemble information, but map it onto the NHC official forecast errors. Next slide. So the model is basically a machine learning method, and Libby's method, instead of just trying to predict like the actual error, it predicts the entire distribution all at once with machine learning. You have to assume an underlying probability distribution for that, which simplifies the problem some. But it does enable a way to take ensemble information and other storm information and predict the entire distribution. And then once you have that, you can calculate a lot of derived products from that. And one of the nice things about it is that we can train this to reproduce the NHC official forecast errors rather than just trying to predict the error of a consensus or a particular model. And so the end result is a set of error distributions that is mapped to the NHC official forecast error, so everything will be consistent at the end. Next slide. So it's basically this is a schematic of how the intensity model works. There's some inputs from different models. These could be ensemble tracks. These could be individual deterministic model tracks. And then the idea is that the errors could be a function of the synoptic environment as well. For example, HWRF might work better in low shear environments or statistical models in high shear. So the machine learning would learn that with the inputs from the storm environment. And for intensity, we assume it's kind of a generalized normal distribution called the SHASH distribution that allows some skewness. Next slide. For track model, it turned out we tried some different things, but the old bivariate normal distribution seemed to work well for the track error distributions. It can't do bifurcation, but the NHC track forecast errors tend not to have that. So it provides kind of a general distribution that fit pretty well the NHC forecast errors. Next slide. So the first version of a TCANE, it has 4 track model inputs, 4 intensity model inputs. I list them there. HWRF, GFS, European Center, UK Met for track, and 2 statistical models, HWRF and GFS. We haven't adapted this to HAFS yet because our first step, we wanted kind of a long training sample, and HWRF has been around for a long time, and as people have shown, it's very good. We'll have to transition this eventually, but the experiments we did this year included those. And I mentioned the an early run is just trying to predict the error of the 4 model consensus, and then the late run actually predicts, after the NHC forecast comes out, predicts error distributions of the NHC forecasts. Next slide. So we had some meetings with Pablo and Wallace from NHC and came up with a set of 4 graphical products, 1 for track and 3 for intensity. We also are working on some explainable AI products so that you understand why the algorithm did what it did. We don't have those on the website yet. Next slide. So this is an example of the an example from Hurricane Helene of the on the left side, the early run that estimates the uncertainty. And one of the things that Wallace suggests is that we wanted to have a reference to the climatological error distribution. So those dashed lines are what the typical error would be if you didn't include the situational dependence. And it was kind of interesting for Helene that it was it was about average difficulty, except as it was approaching the coast. Both the early version as well as the late version predicted as it was making a left turn and the timing of that right hand or the left hand turn, there was a lot of uncertainty into that. And that turned out to be true. That's the place where near the landfall is where I think the uncertainty was the greatest. Next slide. These are some examples of the intensity error distributions. Again, on the left is the early and the right is the late. And for Hurricane Helene, it was pretty interesting, the 48-hour forecast. If you look at the intensity distribution at 48 hours, there was only like a 1% chance that Helene was going to be weaker than the 4 model consensus. It was like 99% chance it was going to be bigger than that. And on the right-hand side, that was also showing that the NHC forecast, the errors were, the intensity was probably going to be bigger than what NHC did. I think Mike Brennan actually said that on Monday. He said that his advice was that if you're going to go big, go bigger. And this statistics would have provided some support for that. That Helene was just really going to go, looking at the characteristics of the 4 models and the really favorable environment that this storm was moving into. Next slide. Some other products. These are just the probabilities of a category 1, 2, 3, 4, or 5 hurricane compared to climatology for that same Helene case. And I guess if you just focus on the purple line there, probability of category 4 was greater than 60%. And then and the same thing with the late model. It was just everything was pointing to this to being a really strong storm. Next slide. Since we have the entire error distribution, we can also use this to forecast rapid intensification. And it turned out the probabilities for rapid intensification at these different thresholds was very high, 60 to 80%. And just for reference, we have the SHIP's RII probabilities on there, and the product on the website will have that as a baseline for comparison. Next slide. The real-time website, basically we're running it in 2024 in near real time. Go ahead and move to the next one. This is there's a subset under wind hazards on TC real time that has all 8 of the products that I just showed, the track uncertainty and the 3 different intensity products. We started this pretty recently, but we're going to backfill the entire season so we can look at these in some detail, and these will be live in 2025. Next slide. And I think I'll finish up here with just some verification. These were completely independent runs. The training had never seen these before. So we looked at 2 verification measures, reliability and error spread relationships for the Atlantic, and we also ran this in the East and Central Pacific. Next slide. So we're just looking at the reliability of the 67th percentile ellipse and the 80 percentile ellipse. And the bottom line of this slide is that the red bar should exactly go to the dash line, and the red dash line and the blue bar should go to the blue dash line if it was perfectly calibrated. And the Atlantic intensity and East Pacific track were very well calibrated, where the East Pacific and intensity Atlantic track were a little bit under dispersive. Not as, like if you take the ellipse, there were more forecasts outside of the ellipse than there should have been in that count, but it's within 5 to 10% for both of those categories. So I feel like that's a pretty positive result, is that it's fairly well calibrated. Next slide. Oh yeah, there should be one more. Oh, there it is. The error spread relationship, this is just looking at if when the distribution is wide, the errors were big, and if the distribution is narrow, the errors should be small. Next slide. And so that turned out to be very true for track. If you look at, you just divide the interquartile range into low, medium, and high, and then compare that to the distributions. It's a pretty monotonic relationship. The big errors was when TCANE said the errors were going to be high, and they were small when it said it was going to be small. So that's a very positive result. Next slide. And it worked pretty well for intensity too. Wasn't as dramatic for track, but still it's a pretty good indicator of the track and intensity expected errors, both for the consensus for the early runs and also for the NAC forecast itself. Next slide. So a summary is that we ran TCANE in real time 2024. Generally good reliability, a little bit under dispersive, but the sample is not that big. The error spread relationships are very good. And what we're going to do in the last year of the project is that we want to, we said we would develop a version for the Western North Pacific, because if we use this in the wind speed probability model, that includes the West Pacific domain. And then we also want to test this as input to the wind speed probability model. So can we sample from these error distributions to get the situational dependence into the NHC official forecasts? And so that's the thing that we'll test in the final year of the project. Thanks.
Thank you, Mark. Our next presenter is Ryan Torn, and he'll be sharing updates about his work expanding the ensemble-based sensitivity to TC hazard forecast.
Okay, thank you. Can you drive that in the room, or do you want me to drive it?
Do you want to try driving, Ryan?
Sure. Okay, can you see my screen now?
We can see it, but it's not full screen.
Yep, I'm just moving that now.
Looks good.
All right, thanks. So yeah, this is a work that was a follow-on to a JHT project that was funded in the last round of trying to expand our sensitivity guidance from just track into hazard forecasting. And I'll just thank both the people in NHC who have helped on this, particularly Wallace and Alan, as well as Lisa and Philippe for providing some input on this. All right, so sensitivity analysis is a way of providing objective information about where observations should be taken to impact a given forecast outcome, such as track or intensity or wind speed or precipitation. So as I said previously, we developed some methodology using ensemble-based sensitivity for tropical cyclone track forecasts. But what we wanted to do was use the same methodology now to expand this toward hazard guidance. So are there situations where, you know, the distribution, the uncertainty and the hazards may be different from where you might go for track. And so the goal of this project, as I said, was to expand this ensemble sensitivity package into TC intensity, wind speed, and precipitation forecasts. And just so to do that, we had to develop some metrics for measuring the intensity, the 2D wind field and precipitation, and have it do it so in an automated way. It couldn't be something that a forecaster would have to always go in and do themselves. The second goal was to provide some daily real-time ensemble-based sensitivity guidance for aircraft operations using ECMWF and GFS ensemble output, and updating our Python package that does all of this stuff. So if you're not familiar, ensemble-based sensitivity is a linear regression technique using ensemble forecast output, where the dependent variable, is some sort of measure of the forecast. So in this case, it could be the tropical cyclone track, its intensity, wind field, or precipitation. And the independent variable is a forecast field at a given location at an earlier lead time that you want to see how changing that forecast field at the earlier time impacted the forecast. So for example, in the track situation, we were often looking at how does changing the steering flow at some location around the storm impact the subsequent track forecast. As we go into these other metrics, we had to actually start to evaluate which fields were most appropriate for each of them. And so, as I said earlier, since 2018, this ensemble-based sensitivity guidance has been used by NHC to draw some of the G4 flight tracks. This was accepted for transition into operations in December of 2023, so I'm quite happy about that. And that previous methodology used a time-integrated track metric, which looks for the precipitation perturbation within the ensemble that explains the most variance. And so what I'm going to show you here is an example from Hurricane Helene from the 0 UTC on the 24th ensemble forecast. The black solid line here is the ensemble mean track. The gray lines are the ensemble member tracks. Each of these, each colored dot is the positions every 24 hours. And this dashed is this time integrated track metric. And so this is calculated to an EOF decomposition of the track position forecasts. I won't get into the details here, but basically, in this case, the metric is a Helene being a little bit to the right of the track and then getting substantially more to the right of the track as the storm makes landfall. So I'm going to show the rest of the talk is me showing examples of this from this particular forecast. And so this is an example of the output from the track metric. Here, I'm going to show a lot of figures like this through the rest of the talk. So I'm going to just kind of describe what this is. Here, the contours are the ensemble mean steering flow vorticity, where solid contours are positive relative vorticity, dashed is negative relative vorticity. And the shading is the sensitivity of the Helene track forecast to the steering flow vorticity at this time. This is a time of the first G4 flight associated with Helene. So here, positive values mean that if I increase the vorticity at that grid point, I'm going to get a Helene forecast that is more to the right of track of the ensemble mean. The negative, the cold color shading is indicative of if I increase the vorticity at that point, I get a track forecast that is more to the left of the ensemble mean. So taking away the labeling here, you see that there is kind of 2 or 3 main regions of sensitivity here. One of them is associated in the eastern Gulf of Mexico with the strength of the subtropical ridge. such that if I increase the vorticity there, weaken the subtropical ridge, Helene drifts a little bit to the right. The second area is in this dipole pattern around the upper level trough that's over the central US, such that shifting that to the southwest is associated with a more track to the right. And then a little sensitive region out here over the Bahamas as well. And so if I overlay where the dropsons were deployed for this particular mission, you see that they more or less perfectly aligned with where the track sensitivity was, because this information was available to the Hurricane Center forecasters at the time. So for this project, I said we're extending to some other metrics. So for intensity, we do something very similar we do to track with an EOF decomposition of the time integrate of the intensity forecast measured in the minimum pressure. That works a little bit better for modeling cases. And so this is a case where the positive value of the metric is just a more intense storm up until landfall. The 2D wind speed metric, we do the maximum wind speed and we do an EOF decomposition over a adaptive domain. And so this is what's shown on the right here. So the shading is the ensemble mean maximum wind speed through the forecast. And the contour is the EOF decomposition that's done on that. So positive values of the metric are just the stronger winds to the right of the mean position of the storm, and especially right along the Florida coast. And then finally, we have a precipitation metric, which was quite useful in this particular case. Again, picks out an adaptive domain, looks for precipitation over land, and then does an EOF decomposition of that precipitation forecast, which is shown in the contours here. Shading is the ensemble mean precipitation. In this case, positive values of the metric are going to be associated with an eastward shift of precipitation and more precipitation over the Appalachians in North Carolina, which saw a lot of precipitation in this case. So now let's go through and look at the sensitivity of each of these metrics to the steering flow vorticity at this time. So this is for the intensity metric. You see that there's a lot of sensitivity to the steering flow vorticity over the Gulf, such that if I weaken the subtropical ridge here, I get a stronger storm in the forecast, which again lines up well with the dropson locations. Wind speed shows something very similar. Again, weakening the subtropical ridge, stronger winds in the forecast. In addition, there was some sensitivity into the water vapor, the mid-tropospheric water vapor to the east of it over Cuba for this particular case. This is the moisture that gets wrapped into the storm later on as it gets into the Gulf of Mexico. The interesting one is precipitation in this case. So this is the sensitivity of the precipitation forecast to the steering flow vorticity. And you see that there's, in this case, almost no sensitivity to what's going on in the Gulf of Mexico. All of it is in the position of the upper level trough over the central US, such that if I shift that to the east, I get the eastward shift in the precipitation distribution. So saying that some of these details of where the precipitation sets up is really focused on the upper trough and not in what's going on in the Gulf of Mexico. And if we can flip this over, this is the GFS version of that particular sensitivity product, and it shows something extremely consistent with what was in the ECMWF. So at least in this case, there's a lot of consistency from depending, the results don't depend on which model you use. In collaboration with my NHC colleagues, we've developed this dashboard version of the product, which shows all four sensitivity to all four metrics at the same time in this paintball format, where each color is sensitivity to a different field. The idea is that you really want to be deploying aircraft or deploying dropsons where all of these areas overlap with each other. I think you can see that it does in this case. Working with Alan Brammer, we've also gotten these gridded, this paintball version into the AWIPS cloud, and that's was being pulled in there pretty much the entire season, at least in the second half of the season. So that capability is also there. The next thing that we need to do is get this actually, the sensitivity code running at NHC. They're still pulling that data from my computing system. And so just to wrap up here, we can see that this ensemble sensitivity technique can be extended to calculate the sensitivity of track and TC related hazards. The automated metric that we use, it proved really robust, and there really doesn't need to be any forecaster input to define them. Ran real time in 2024 for all Atlantic, East Pacific, and Central Pacific storms. Most cases, it was aligned very well with the track sensitivity, but we'll be continuing to refine this dashboard based on the forecaster input, get this over to NHC for further testing, and I have a graduate student who's also working on some more in-depth case studies, including some verification work. So with that, I'll wrap up and thank you, and hope to hear some questions later on.
Thank you, Ryan. And our last presenter for the session is Sarah Ditchek from the University of Miami, and she'll be sharing an update about the work she's doing about targeted dropsons on TC forecast and HAFS.
So I'm going to keep my camera off for this because last time I shared my screen, my presentation froze and nobody wants it at the end of the day. So let's hope that that works. Okay, can you see my slides and hear me okay?
Yes.
Great. Okay, so what I'm going to be showing you today is some preliminary analysis from a sensitivity study on the impact of G4 Recon to HAFS version. So how do we get to this project? So NOAA's G4 flight track strategy was recently modified. In 2017, the typical G4 surveillance pattern was just one outer ring circ around 330 kilometers from the TC center, as well as environmental targeting described by Aberson in 2003. Since then, there have been two main changes. The first is this new inner ring circ around 165 kilometers when possible. And the second is a new way to guide environmental targeting, which you just heard about based on Ryan Torn's ensemble sensitivity metrics. So the impact of these changes on TC forecasts need to be quantified so that we could figure out ways to further optimize the strategy. We could assess those ways. And these results and optimizations can be delivered as guidance to HOT and NHC for use during G4 flight track planning. So for example, let's say that the results show that the G4 is most impactful when flown in a tropical storm, but not as impactful when flown in a hurricane. Well, guidance delivered will indicate these distinctions. At least that was the plan. So the original project plan was to quantify the overall impact of G4 Recon on TC forecast by using HAFS G1A. To do so, I ran two experiments. The first is the control. It's HAFS out of the box. It's called all R. In terms of what recon was assimilated, it assimilated recon from the C-130, P3, and G4, shown here in red, blue, and green, respectively. The second experiment removes the G4 recon entirely. It's called the no G4. In other words, only C-130 and P3 recon are assimilated. Otherwise, both experiments assimilated all operationally assimilated conventional and radiance data. So when we conduct studies like this, we want to have the largest sample possible. That's most ideal since there's a lot of variability present from forecast to forecast, TC to CC, and year to year. So I identified every TC between 2020 and 2023 that had tasked G4 missions and associated GFS input data. And in total, there were 15 of the TCs, all in the North Atlantic Basin. And those are the TCs listed in this table. This resulted in 469 cycles covering 56 total G4 missions. So the main result found was that for track and intensity, G4 Recon generally improved tropical storm forecasts, but degraded hurricane forecasts. And you can see that here below. These are consistency scorecards for forecasts with G4 Recon stratified by initial classification. You have tropical storms on the left, hurricanes on the right. Your x-axis is your forecast lead time. The y-axis is the variable, track, Vmax, or Pmin. Green boxes indicate improvement, red boxes indicate degradation based on the consistency metric color bar below the graphics. And for more details, check out our WAF paper at the QR code on the slide. So in general, what we see is that G4 Recon improves tropical storms forecast, particularly for track, but for hurricanes, directly sampling with the G4 wasn't found to be beneficial, particularly for intensity. After digging into these results a bit further, we came up with two potential explanations. So the first relates to the DA sophistication in models. Recent research found that the impact of recon on TC forecasts is strongly dependent on covariance choice. This project was using HAFS, which uses global covariances, so the forecast degradation found in hurricanes might be indicating a non-optimized DA system. We thought this could especially be true since the performance that we see in hurricanes here is emblematic of earlier results retrieved with HWRF before the cycle DA system was implemented. We have another potential explanation, and that's the HAFS version used. So Jason Sippel conducted some recon versus non-recon experiments with both HAFS V1A and B, and he found that recon impact differed. This project uses HAFS A based on its 3 years retro performance, and given the differences that Jason found in his experiments, we believe then that our results might differ if rerunning experiments with HAFS B. And that was something actionable that we could relatively easily test by rerunning these experiments with HAFS V1B. And so that's what we did. And so this is a new project plan snapshot, what I'll mainly be discussing today. So all new items are going to be in teal. The new objective is to quantify the sensitivity of the impact of G4 recon to HAFS V1 version A or B. The experiment suite and data that is or is not assimilated is the same. There is a slight difference in scope though. So all of these runs did on Orion. Orion switched over to Rocky 9. And before that switch, I was able to rerun all TCs with HAFS V except for one, Isaias. And since analysis is performed on a homogeneous sample following NHC verification rules, you can see the reductions in sample size here given that change. Okay, so before getting into the results, I did first want to put in context the number of G4 OBS that are assimilated in the set of experiments. So G4 recon made up 25% of the total assimilated recon OBS. You could see that breakdown of recon by TC here on the y-axis and number of OBS on the x-axis, and this graphic is valid for HAFS A. HAFS B values are quite similar. Now, over our sample of 14 TCs, there were just over 3 million recon OBS assimilated. And what you see now is the experiments when you remove the G4 recon, you can see the reductions now on the right. We're down from just over 3 million to just over 2 million. So the G4 recon mainly flies in the synoptic environment, again, though that inner circ does sample the near storm environment. And so if we took a look at the percentage of G4 recon that was removed in the no G4 experiment, around 71% of the recon in the synoptic environment was removed, compared to 20% of the near storm and under 3% in the inner core. Now, given the detrimental impact found when G4 recon was assimilated in hurricanes in HAFS A, the very first thing I looked at after these experiments completed with HAFS B were the performance by initial classification. And so what I found was that while G4 recon generally degraded hurricanes in HAFS A, it actually improved those same forecasts in HAFS B. So you can see that here below. These are, again, our scorecards on the left from HAFS A, and on the right from HAFS B. I'm not just showing you track and intensity as I did before, I'm also showing the size variables. And so let's break this down. So first, for hurricanes here, I'm highlighting for track and intensity. You could see that hurricane forecast in HAFS A that had that degradation I talked about in an earlier slide on the left. If you look on the right to the same forecast in HAFS B, we don't see similar degradation. We actually have some improvement. Also, G4 recon improved R34 and R50 HAFS B forecasts on the right that wasn't really seen in HAFS A. And also, while tropical storm performance between models was broadly similar, even tropical storms had some improvements in HAFS B over HAFS A, but it wasn't as nearly as stark as the hurricane contrast. So what was driving this hurricane degradation in A, but the hurricane improvement in B? So digging into that, it was actually Hurricane Lee that drove most of the disparities between the HAFS versions. And so for a representative example, I'm going to use VMAX results to demonstrate this. So these were the consistency metric outcomes for the lead times with the differences. HAFS A is going to still be on the left, HAFS B on the right. What you're seeing now is the percentage point contribution of each TC at each lead time to the overall MAE skill. Essentially, if you add up any column, it equals the composite MAE skill for that lead time, which is shown at the bottom. This type of graphics helps you see if any of the TCs were driving the MAE skill results. To more easily compare performances between HAFS A and B, I'm now showing you the percentage point change between HAFS A and B. So first, if we look at the very bottom row here, the composite average MAE skill increased 16 points in HAFS B compared to HAFS A. And nearly all of this improvement was due to one TC, that's Lee. You can see here, if you go up one row, that Lee had a 13-point change between A and B. But it wasn't just Lee. There were yes, it dominated the results, but several other storms did contribute, like Fiona and Laura. So by the point in time when these results were analyzed, HAFS V2 was operational. And with that upgrade, as we've heard of the last 2 days, there were various DA, VI, and physics changes. So given the disparities between the versions, and since we want to make sure that any guidance given on the impact of G4 on TC forecast is the most up-to-date, we decided to rerun our experiments with HAFS V2. In doing so, we ran TCs in the order of that contributed the most to the disparities found in V1, So what that means, we started with late. So far, a total of 6 TCs finished. So I'm going to show you composite results for those. But first, here's the project plan snapshot. Differences include the fact that I am running with HAFS v2. On that, so far, only 6 TCs finished running: Delta, Henri, Sam, Fiona, Ian, and Lee. And again, since these were the TCs that contributed to the most of the disparities found for hurricanes between the HAFS v1 versions, I'm just going to be showing you the hurricane results. Okay, so let's take a look at the G4 impact by upgrade and version for individual forecasts that were of hurricane strength at 0 hours and that assimilated G4 recon. Again, results that I'm showing you are just for 6 TCs, 8 still need to be run with HAFS v2. And the sample size of the results I'm showing you are going to be different. But that being said, HAFS v1 had 60 cases at 0 hours compared to 45 cases at 0 hours for v2 so far. So they're more similar than the number of TCs left to run might make it sound. Now, let's first look at the differences within upgrades. So here are the scorecards for HAFS A, v1 on the top and v2 on the bottom. The track and intensity results improved in v2 compared to v1. That short lead time degradation for track and intensity is now gone. There were some outer wind radii improvements found too, particularly for R34, as you could see by those dark greens. Now looking at HAFS B scorecards on the right, for HAFS B, there were more similarities between the different upgrades, but the impacts were magnified. And what do I mean by that? So for example, if you see on the top here that I've highlighted in blue for V1 for R50, there was some R50 improvement. If we look now at V2 down below, there was more R50 improvement in V2. So that's what I mean by magnified. And it goes the other way too. If there was some degradation, like for Pieman in V1, there was more degradation for Pieman in V2. So the disparities in track and Vmax for V1 up top that I talked about in the last section were minimized in V2 on the bottom. You can see that the track and Vmax on the left and right for V2 for HAFS version A and B were more similar. And this is a positive result for track, since we'd hope that having recon in the synoptic environment, like that from the G4, would benefit track forecasts. Now, the disparities in outer wind radii between versions were similar, with HAFS B outperforming HAFS A. Again, with the G4 flying in the synoptic environment, we'd hope for better outer wind radii performance. And here, HAFS B seems to be handling that recon better than HAFS A. But near the inner core, HAFS B struggled. G4 recon degraded both the Pieman and R64 at nearly all lead times. And this occurred in V1, but was even more apparent in V2. Now again, these are hot off the press results. ATCs still need to be added to the sample, so there are caveats here. And I have a lot of other things that I need to look at. So we'll see if the story changes at that point. But I did look into the TCs that were driving the results so far to see if Lee was the main driver like it was for V1. And it wasn't. It was more equally split amongst the TCs. Now, before summing up, I did want to dive into the outer wind radii results, actually, because they were very qualitatively similar between upgrades and versions. Now, on average, G4 recon is making TCs larger. And to see that, let's look at the bias characteristics. So first for R34 on the left, up top here, the consistency metric outcomes. This is going to be for HAFS V2. This is versions A and B. Now, below that is a bias. V2A is the solid lines and B is the dashed lines. The x-axis is your forecast lead time. The y-axis is your bias. The green line is your all R experiment that included the G4 recon. The red line is your no G4 experiment, which denied the G4 recon. And we see that TCs in V2A were too large, and the G4 recon made those TCs larger. But this made the forecasts worse. And this was particularly true through 72 hours. In HAFS V2B, the G4 recon again acted to make the TCs larger, but since TCs in V2B were too small initially, the G4 recon actually made those forecasts better. And here are the results for R50. TCs were initially too small for both HAFS versions, with HAFS V2B having a larger small bias than HAFS V2A. And while the G4 recon made TCs larger in both versions, it reduced the bias more in B. And this led to more improvement in B than in A. And note that these same types of bias trends were also found in HAFS V1. So to summarize, the objective of the work is to quantify the sensitivity of the impact of G4 recon to HAFS version. Again, this slightly changed from the initial objective and goal of this project. For the main takeaways, we found that for HAFS B1, G4 Recon generally degraded HAFS A forecasts, but improved HAFS B forecasts. And when stratifying results, we found that this was driven by really hurricane forecasts that were degraded in A but improved in B, and Hurricane Lee drove most of the disparities. For V2, the G4 Recon improved track and outer wind radii, but degraded inner core metrics for hurricanes. And there's no real driver. There was more evenly distributed across the TCs. It wasn't just Lee that was driving these results. And there was some consistency as well here that G4 Recon was found to make the TCs larger. And so I will stop there and I will take questions in the Q&A session. Thank you.
Thank you, Sarah. And now we'll open it up to questions and discussion in the room and online.
And don't feel bad if you don't have any questions. It's been a really long day. We've also had a lot of chatter in the chat boxes during this particular session. And I also do want to mention to the people in the room that everyone always clamors over the churros, but there's an awful lot of them left in the back. So please take them with you since I already paid for them.
Yeah, comment and question for Rob. I think that was the first or second talk. That excellent stuff on them. I'm always excited to see the social stuff and how people respond. But the problem I see, and I've heard from people, especially recently, and talked to Dan Brown a couple of days ago about it, is that you can say, oh yeah, the storm is going to be Cat 3 when it hits you, or it's going to have 110-mile-an-hour winds. But what the public doesn't understand is that not everybody on that path is going to get Cat 3 winds. That's a huge statement. Maybe a very small area would get that, and people get confused because they thought it was going to be Cat 3, and then they get, much less, and they say maybe it wasn't Cat 3. I mean, how can you possibly adjust your typographics to make it clear that this is the max that somebody might get, but you probably won't get that? I don't know if that makes sense how I'm saying it. Okay.
No, that's a good point. And yeah, we could look into changing the, either changing how it's worded, or maybe adding like a little disclaimer down at the bottom that says something to that effect. Like instead of, worst case scenario, the worst case scenario that someone in this area might get, or, worst case scenario with an asterisk, but yeah, that's a good suggestion. We can definitely look into that.
Yeah, okay. Actually, follow up on that is even beyond that. Is in some ways one-dimensional, speaking to a hazard in a one-dimensional way. Really, more important than knowing exactly the landfall and how strong is that landfall is the extent of the hazards. Because, I can tell you that that's what drives decision. What drives decision is not if the hurricane on a landfall as a category 4 or 150 miles per hour wind in the Big Bend. What drives decision is how far away from that is it going to be producing life-threatening storm surge, right? It could be 150, 200 plus miles from there to the south. So the problem when we focus on a metric that speak to the center of the storm, that's too one-dimensional. That's why years ago we walk away at NEC from strike probabilities. The center within so many miles of the location, it means nothing to the decision maker. I'm telling you, it means nothing. For I joined NEC, I was 28 years with a WFO embedded in emergency management, EOCs, helping make those decisions. That means nothing. I'm sorry to be so harsh about it, but I'm providing you a perspective that is real, okay? So from a decision making perspective, I'm telling you that, when we're working now on WSP 2.0, one of the new products we are working on is creating two-dimensional exceedance map, for wind speeds. Because we're trying to draw from the success we have with the storm surge on that side. It has improved dramatically our ability to communicate the risk and help make better decisions. So that's just an input, I think from this kind of work we learn a lot, but I'm telling you, we need to be careful about being two-dimensional too one-dimensionally focusing just on one aspect.
No, I totally agree. And we heard that a lot in our focus groups, especially from meteorologists from WFOs and emergency managers. Like, why are we focusing on wind speed landfall? We should be focusing on inland flooding and on all the other myriad threats, not just this one thing. But that's the product we were asked to evaluate. I don't disagree, but that's the product we were asked to evaluate to see if people actually understood just that basic amount of probability.
Yeah, and I just come back to him. I was only focusing on the wind because that's what I've heard from people recently that they were really bothered by. But of course, the big task is to help the public understand the incredible complexity of the hurricane impact, which has so many aspects.
I think go to the online question, right?
Yeah, Pete, go ahead.
I want to congratulate Jonathan Bai on the analysis he did of the SFMR observations and how he's developed a scheme with together with Michael Bell's objective analysis scheme of combining flight level winds with the SFMR, combining the Doppler radar wind profiles with the SFMR, and getting an optimal set of wind profiles across the storm. This just makes a whole lot of sense rather than arguing about little potential defects in one sensor or another. So I'd like to really congratulate you, John, on that work.
Thanks, Pete. I'll just say it's a team effort, and I'm really glad to be working with such a strong team. So Alex DeRosier and Jen have done a tremendous amount of work at CSU. So it's just really exciting to see this project integrated. But my question's for Kate and maybe Pablo. You mentioned how the incorporation of land use maybe could create a communication problem for people when they think, oh, this wind's only going to be like 50 knots, as opposed to like the 90 knots that's offshore. And my question is, could we just get away from sustained wind and only show gusts over land? And if so, maybe that would fix some of this communication problem, because it's really the gusts that cause the damage, and it's the gusts that people should care about. Sustained wind is a useful scientific metric for certain things like storm surge modeling maybe, but anyway, I'll just stir the pot a little bit.
And I'll note that on day one, it was Mike Brennan noting that all the deaths over Georgia and South Carolina attributed to the wind gusts, right?
Yeah, it's when we started working with WSP 2.0 and Mark showed us the first sample output 5-kilometer resolution, everybody excited about the science work, the feats of accomplishing doing 1,000 members at 5 kilometers. And then when we see the final output, everybody was like, how the hell do we explain this to people? We understand it as scientists, right? But you're telling people to take actions on a very small chance of this wind speed over your location. Very small, the truth is the legacy model has a well-known high bias of wind speed probabilities inland because it didn't have the land effect incorporated. This one does. So it creates that challenge. And definitely what we're beginning to converge, the answer is to start producing wind gust probabilities. Along with presenting the data in a different format, not just a chance that you're going to see this threshold, but 10% exceedance map. But does it look like 5%? Whatever. We're creating multiple of them and prototyping multiple of them, and also seeking help from social scientists. But you're absolutely right. We need to start walking away from sustained wind or just depending solely on that and addressing wind gusts. Here is another secret. In the entire weather service, NAC were the only one who just stuck to sustained winds. Every other wind-related hazard in the weather service that is issued, high wind watches warning, storm warning, is based on frequency of gusts, not just sustained winds. So, yes, we will be addressing that.
Yeah, so this is Shaman from UH. So the question also to Kate about the similar question. So, yeah, definitely WTCMs have a better results over land than before. So my question is for the dynamic model right now, like for example, HAFS AV, and even we have ensemble in the future. how would we use this information, like, because it's more physically complete, how can we use that to predict the surface winds? Because right now we have like a product, like I believe Andy and also Mark was lead that, so they try to have a product that HAFS, right? So they can produce a surface land wind gusts, but it's also a function of the surface mean wind. So the meanwhile, like, so that comes back to the original point. So what do you think the future, or how we can better use this dynamic model for the future land forecast, the wind forecast? I mean,
There's additional work going on as well involving surface wind analysis and reanalysis. We're starting with the observations there to try and combine all of the available observational data sets into a wind field. But there's also, the A in HAFS is analysis. And we're trying to get back to using, comparing that. If we've got a surface analysis of record for the observational side and doing the comparisons with the HAFS analysis as they get the DA spun up, and seeing what, different observations are going in to these different products and seeing if there's a way to bring that back in. But there's also the opportunity further down the road to investigate, like we were showing with the in the wind speed probabilities, the dynamic model ensembles going into the track and the intensity. We can build in the wind structure as well and see how that evolves through these simpler post-processing and see if we've got information there. And I didn't show them here, but we actually have correct comparisons between the HAFS ensemble winds and the WTCM WSP 2.0 winds as well that we've been looking at.
We're going to our last question from Frank because we're already over time on the room.
Oh, well, I'm going to put Pablo and Wallace and EMC on the spot. We heard some great presentations about work that's going to be transitioned. Is this going to get through the funnel, or is the funnel already full? And how will these people be able to get them through the funnel? Give us their advice. Give us advice on how they can make that happen.
Well, I probably have something to say, but you read my mind, and I decided to drop the question. But this link exactly to the section on Monday, the work Vic is doing, Brian Thorne work, and those we figured out we have displaying A with. The problem is transitioning those algorithms, making them operational. Because right now, no, we don't have that bandwidth. It's that, and that's the conundrum. That's the problem that we have.
No, it's hard. We've talked enough about the funnel. I don't want to dwell on it at 5:45. However, however, as you saw, like in Ryan Torn's talk, in Jonathan Vai's talk, a lot of work has been done by folks like Alan to get it really close to the finish line. A lot of these things are running on an experimental or on a development server at the Hurricane Center. They've been prototyped in AWIPS. We're really close. So I think we're really close to the bottom of the funnel on a few of these projects. So there's light at the end of the tunnel. We just got to take it to the finish line.
And as the UFS style guy, the thing that encouraged me most the last few days is that so much of the work is already being done with software which is really close to operations. And that makes a huge difference on the beginning of going through the funnel. Yeah, right. And now we really have to go back to deal with less risk aversion, deal with our end users there. And so this is why we need the social sciences people working with us, how we can get over that. Yep, I agree.
All right. On that note, thank you. All right. We will start tomorrow morning at 8:30 with a session on supplementals, followed by a break, then developer support, then lunch, then on HFIP R2O and O2R, because I know people had talked about the O2R aspect earlier. followed by our last session of future and strategic planning, where we do just 30-minute discussions on different topics looking ahead.